Ma'am will come in few minutes and she will start. Okay.
Can you people see, hear me?
Yes, ma'am.
And can you see the board?
Yes, ma'am.
All right. So last time I have introduced to you the ideas of groups. I mean, at this last couple of lectures, we discussed groups and then also we defined different kinds of groups like abelian groups, finite groups, infinite groups, continuous groups. Then I also defined the notion of a subgroup, I think, and in particular a proper subgroup. So, for example, let me just go back. So, if I have a subgroup, so subgroup is some subset. So, given a group G, I take some subset of this group, and if this subset also satisfies all the group properties with the same group operation, so that's very important. You can't change the operation midway. Then, in that case, you would call this as a subgroup. And as I said, every group has trivially two subgroups. One is with just the identity element, and the other is the group itself. But what we would be many times interested in what is known as proper subgroups. So proper subgroups are those which are neither of these. And for example, if you remember your O3 group, so this is the group of 3 by 3 real orthogonal matrices. And what we saw was that in this case, any matrix here can satisfy, or we'll have to satisfy that the determinant is plus or minus 1. Fine. Now, suppose I say that I consider now the set of all, so it's a set of all R, so all 3 by 3 matrices, real matrices, such that R transpose R equal to R transpose. And so this is the determinant of R equal to plus 2. Now you can see, so if I consider such a set now, this is a set of all 3 by 3 real matrices such that R transpose R equal to I equal to RR. So up to here, then it simply means that each of these R's belongs to O3 because it's simply a real orthogonal matrix. But now that I put this condition, so here we are restricting now to those matrices M in O3 such that the determinant only equals to plus 2. Now you can see that if I have two matrices, suppose I have M1, say R1 belonging to this O3, and say R2 also belonging to O3, such that determinant of R1 equal to 1 equal to determinant of 1 plus 1. Okay. So if I combine now these two matrices R1, R2, now because of the fact that these belong to this O3 group, this will also be an orthogonal matrix. What will be the determinant of this resulting matrix R1, R2? If R1, determinant of R1 is 1 and determinant of R2 is plus 1, then what will be the determinant of the resultant matrix R1, R2? So 1. Because you know that determinant of R will be determinant of R1, R2, which elementary ideas about determinants tells you that it should be equal to this. Or in other words, if I'm combining two matrices with determinant plus 1, then I'm going to get a resultant matrix again always with determinant plus 1. Now, does identity belong to this set?
Yes. Yes, ma'am.
Identity belongs to the set. And you also know that if determinant of R1 equal to plus 1, what is the determinant of R1 transpose? Okay, given a matrix, if it's a real matrix, yeah, it has to be the same as determinant of R1, no? Because it's a real matrix. And you also know that from this relation that R1 transpose is nothing but the inverse of. So given a matrix R transpose is the inverse of R. So that means identity belongs to this set, and if for any R belonging to this set, the inverse also belongs to this set. So therefore, this set is closed under this definition. Alright. And this is the same because we are again doing matrix multiplication, so I have not changed the group operation. So this particular group, which we'll call it as SO3, this is therefore a proper subgroup of your group. Okay. So this is a proper subgroup. So it's an example I'm telling you of, because it contains more than the identity element. So it's not a trivial subgroup, and it has all those. So whatever, if you remember in our tensors, what I was calling as a proper rotation is essentially a matrix which belongs to SO. Okay, and again the labeling is, what is the meaning of this? As I said, this 3 means you have 3 by 3 matrices, and here O means orthogonal, and here S stands for special. So these are special orthogonal matrices, and the special essentially tells you that the determinant of the matrix is +1. Now let me ask you the question that suppose I consider now this set. So I again consider the subset of orthogonal O3, and I say that I want to have all 3 by 3 real matrices such that this is satisfied and determinant are equal to -1. Will this be a group or subgroup?
No, ma'am.
Why not?
Ma'am, because closure property is not satisfied.
Yes. Because if I combine 2 matrices with determinant R equal to -1, from here you can see that I'm immediately going to get a matrix with determinant R equal to +1. So this is not even, it's not a group or it's not a subgroup. Okay? So this subset, so it's not a subgroup. And you can also see that identity will not belong to the set because identity has determinant R equal to +1. So if it has to be a subgroup, the identity must belong to it. Okay, so this was just to show you a little bit more. This, all right. See, but I also want to point out that see, why are you talking about subgroups? The idea of talking about subgroups is to partition the. So let me go to a simpler example. If you remember this example which I gave you, 1I -1 minus. Now in this, if I consider this set 1 minus 1, you can see that this is a subgroup of this. Okay. Now I can ask that, can I just write my group in terms of, okay, so maybe somebody can tell me, can I write my group as a sum of many different subgroups? Without any redundancy. Is it possible for me to do that? Yes or no? Okay, can you at least tell me one element which should necessarily belong to all the subgroups?
Identity.
Identity. Okay, so it means that I can't write also, it's not possible for me to partition this into, so I can't write it like this, that this is subgroup, this is subgroup, okay? Because you know that every subgroup must contain the identity, so it means that there is a lot of redundancy. So then you can ask the question that, is it possible for us to partition a group into some other objects, into a set of some other sub-objects, such that I can write this as sums of certain objects, sums of those smaller objects. And what you will find is that we can do that by using what are known as cosets. But I will not get into that. I just wanted to mention these words, cosets, and from there you construct what are known as conjugacy classes. So that allows us to partition groups, and I will tell you why that's required without telling you what is a coset or what is a conjugacy class, because I don't have the time to develop these ideas. Because I do not know how many of you are familiar with concepts like equivalence classes and so on. That's why I'm not using that. But I just wanted to mention these words, cosets and conjugacy classes. The reason I wish to mention is, as I said, the final application of any, for us at least, as far as we are concerned as physics people, is by doing what is known as a representation analysis. or studying actually the representations of groups. So what is essentially what do we mean by this? So given a group G, so let me tell you why we are concerned with it, or when I say why we means, I mean as this. So we have, again, let me go back to my example here, that equilateral triangle example. Okay, this is the way I put one. All right. So we found that I can write down the symmetry group for this in terms of the identity element. Then I had this R, R prime, and K, which we defined earlier. So I had these set of 3 or these 6 basic operations, and any combination of this will lead. So these 6 basic operations, as well as any combination of these operations, will lead this triangle, equilateral triangle in the. Now imagine that at the corners of this equilateral triangle, I have say some atoms in it. So I have say some. So now once I say that I have atoms sitting on such a, or at the corners of such an equilateral triangle, so you can think of this as, for example, some molecule which is made of 3 identical atoms which are placed at the corners of such an equilateral triangle. So this now becomes a physical system. Right? Now, once I have a physical system, then what do I want to study about the physical system? So imagine now that I have atoms, and then I want to study, I can ask the question now that this molecule is there. So can this molecule have an electric dipole moment? Or will it have a permanent electric dipole moment? Or I can even ask the question, can it get polarized in the presence of an electric field? And if so, what will be the polarization? Does it have a magnetic moment? Does it have a quadrupole tensor field, electric quadrupole tensor field or not? Because there are atoms, means there are electrons here, there are ions, I mean, there's a nucleus and there are electrons. So I think for now, let's just thinking about the electronic combination. So basically then when I say that I have this physical system of these 3 atoms, identical atoms placed at the corners of this equilateral triangle, then I want to study therefore the different physical observables of this system, which could be, as I said, could be an electric dipole moment, or maybe an energy, or the various energies for this system, or magnetic moments because electrons are spins, quadrupole tensor fields, and so on and so forth. Because what will these tell us? These physical quantities will tell us about how the system is going to behave. So, for example, if I know that the system has an permanent electric dipole moment, then I know that it will have a definite orientation for my charges. That means it is not symmetric or it's not inversion symmetric. Parity is broken. Similarly, if I have magnetic moment, it tells me that this system is going to be susceptible to the presence of a magnetic field. It is going to respond to a magnetic field. If it has a quadrupole tensor field, then it will tell me a little bit about already I told you that when I have a quadrupole field, I get an idea about the shape of the system. And in fact, it will tell you a little bit more about whether there's a bulge somewhere, so whether there's a bulging here or not. Because remember, now these are atoms, electrons, so there are fluctuations because the atom is not going to just sit in one place. When I say that it's here, this actually means the equilibrium positions. But there are electrons, so there are really dynamical quantities there because the electrons can move. Even the ions can move slightly. So there are lattice vibrations here, and there's also this electronic motion. Both are. Okay. So now, basically, then, if you think about this as a quantum mechanical problem, then what you wish to ask is what is the wave function for such a system? So I suppose I'm only interested in the electronic wave function. So I would want to find out what is the electronic wave function for this whole system. And for simplicity, let me just assume here that I just forget about whatever the internal structure. I just think about these atoms or just think about the ions themselves. So you can think of just think of electrons here or just think of these as ions. I'm only going to worry. So in this case, let me say that I'm only going to worry about the ionic motion, not even about the electrons. Then you can say that this wave function should be So for each of these now I have a wave function because each of these ions can move. So for example, I can have motion along the y-axis and along the x-axis. So this can move along, and let's say that this can move along this x-axis, y-axis. Here similarly, this atom can also move x-axis, y-axis. And then so this let me call this x3 and y3 because this is 3, x1, y1. And let's say that this is x2. We are only allowing it to move. I mean, the way I have drawn it, I'm only allowing for motion along the plane. I'm not talking about the z, the motion along the normal to the plane. But in principle, actually, it can vibrate along all the three directions. Okay. Now you can say that the whatever is this wave function should be something. Okay, let's say this. So if I forget about these two atoms, just imagine your quantum mechanics one which you have studied. So I just have one atom, and so it's one particle, and that one particle you're allowing it to move either in the x direction or in the y direction. So what should be the vector space? What will be the dimension of this vector space? Or typically, suppose I want to write down the wave function for such an ion, what will it be? Imagine that there's no other potential; it is simply free to move. Okay, I will make it even more simple. Suppose I have a particle and I allow it to move only along the x direction. Most generally, how can I write down the wave function? What will it depend upon? Okay, in quantum mechanics, how do you write down the wave function? Or one-dimensional wave function?
I'm either using exponential or trigonometric functions.
No, I don't use any particular basis. Just give me a notation. I just want you to write a notation. That's all I'm asking. It should depend on the functional dependencies I want. That's all. Psi will be a function of x, right?
Yes, ma'am.
In this case, psi will be simply a function of x. Here, what will it be? In this case, what will it be? It's going to be a function of x3, y3. Because it will be a function of the x, because this wave function now will depend upon the x coordinate as well as the y coordinate. Is this correct?
Yes.
Okay. Now, if I take in one dimension, this psi of x, of course, you can expand. Suppose I just take a one-dimensional wave function. This, in one-dimensional space, this, of course, you can write in terms of some basis sets, okay, which are like some phi of x, phi n of x, and some ans. Okay, this I can write down. But now, if I have this, what will I get? I will get this as something like a n. So I write this as a n n. So I will have some. Okay, maybe I'm just writing it just to show you this. So my basis functions themselves now will have x, y dependence, and then I will get a. Is this correct? I can make an expansion like this. See, for example, if you put a particle in a box, if you put in a single one-dimensional box, your basis functions are like what she was saying, trigonometric functions like sine and cos. Now, if you put it in two-dimensional box, what will be your basis functions? You will get, for example, sine pi by L x times sine pi by L y, and then all possible combinations. That means you will get a basis set which is belonging to the. Suppose I take it as my length of my box is this, so I'll get like sine pi by L x, so n equal to 1, 2, 3, so on. So this is say the basis set for the one along the x direction. Similarly, I will also get another basis set for the y direction, and I'm taking a square box, so I'll get something like this. Then these phi n's in this particular case will be products of these. So I can get with n, all possible nm. So really speaking, I will have to combine these two vector spaces. Or I take products of these two vector spaces and then I can use these product functions as basis functions for this. Fine. Or essentially what I'm trying to tell you is that what I can do is I find out what is the vector space for this, for example. So suppose a wave function here, my psi here, for psi c belongs to some vector space BC. Similarly, I can find out what is the vector space for the atom here, which will be, say, psi A will belong to the vector space B. And psi B also similarly belongs to this. So the combined system psi, if I have, I can write it as belonging to, the full vector space for this. So the vector space for this full system will be, can be written like this. And my wave function then psi can be written as a tensor product of the wave functions, each of them. Fine. So if I want to find out, so given this physical system now, if I wish to find out any information about this system, this is now a quantum mechanical system. If I know this full wave function for this system, then I know everything because I know that any physical observable can be written as the expectation value of this wave functions. Or we can relate physical observables to operators, and then if I want to make measurements or relate to experiments, I calculate the expectation values of those operators. Now now I can also say that this wave function for this combined system must belong to the direct sum of these vector spaces. So if I ask you what is the dimension of this vector space, then the dimension of this vector space will be the sum of the dimensions of each of these vector spaces. Okay. So now let us ask the question that now we found that this particular equilateral triangle remains invariant under any of these transformations or a combination of these. I don't have to worry about the combinations because it's close. Because if I do a combination of this, I know I'll get a result in one of this. So I just have to worry about what happens under each of these transformations. And what we have seen is that this triangle remains invariant under any of these transformations. So now I can ask the question, what happens to this wave function when I do any of these operations? How does my wave function change? Because I'm performing such an operation here, physically, say for example, we make a rotation by twice pi by 3 anti-clockwise. So I know that this goes here, this comes here, this comes here. Then I can ask what happens to this wave function. See, this I've just written formally. I've not told you exactly which way I'm combining them. Because here I'm making a combination of my total wave function by combining the wave functions for the atom at A, at the vertex A, B, and C. And as I've already illustrated with the square box example, I can get different ways. So if I combine, for example, in that square box example, the xy's, if I take the lowest states, I'll get sine pi by Lx, sine pi by Ly. But I can also get sine pi by Lx, sine pi, twice pi by Ly, and so on. So what this means is that this wave function can take, there's a variety of different ways it can take, and then, which also tells me that there are different ways of getting or finding out what these transformations do. But we can boil it down then, because we know about vector spaces. What I can do is, given a vector space, whatever is this psi, I can expand this psi in some basis of V. Okay. So I can say that my psi is going to be, whatever is this psi will be. So let's assume that my basis for V. So let me now take that, suppose let us take, I'm now going to do a little bit more general case. So assume that my physical system is there and I want to find out the vector space in which that wave function is operating. And let's say the dimension of that vector space is D, suppose it is. Then you know that I can get a basis set E1, E2. So I have some this thing and I have to put these such basis vectors. So let this be my basis for. Then you also know that my psi then can be written as sum an En as a linear combination of this n equal to 1. This you know from your vector spaces. And further, I mean, what I've shown you here is further what is possible to do is that this vector space, your overall vector space, very often can be decomposed into sums or direct sums of vector spaces which are smaller dimensions. Right? Okay. Now I can ask the question. As I said again, if I make now a symmetry, so this is why we call this as a symmetry transformation, because we call this group here as a symmetry group for the equilateral triangle, because it leaves it in the same way, or it leaves this whole system invariant. Please remember here I need identical atoms if I want to make connections with my physical problem. All right. So then now I can ask that I make this transformation here and I ask what happens to this wave. Now, typically, when I want to change a vector in a vector space, what do we do? Suppose I'm saying that I have a vector. Now, go back to your MMP2. I have vectors. And then what operations can I do on the vectors to change it to something else, which again remains in the same vector space? You have heard of linear operators?
Yes, ma'am.
What does a linear operator do? So you have vector space. So the vector space consists of some vectors. Now, what does a linear operator do on the vectors?
And we transform that vector into another vector which belongs to same vector space.
So given a vector space now, I can also construct some linear operator A. Okay. So you know that if I have a linear operator A, then A acting on some B. So if suppose U belongs to B, AU will be equal to some. So this linear operator will act on a vector and transform it to some other vector. So in other words, what I can see is that if I ask about how vectors are changed, essentially I can think of defining those changes by the action of some linear operator. Now, in the same way, now what I can ask is that, okay, I had the symmetry transformations and I'm asking the question, what happens to this psi or to this wave function under this symmetry transformation? So I can say that I will now represent, okay, this G belonging to G by a linear operator. Rho of G, which will act on So in other words, what I'm going to do now is that, so given this group, so the first thing therefore is that given a physical system, first of all, you must identify, I'm now talking with respect to groups and representations of groups. So I'm keeping our physical systems in mind. So given a particular physical system, the first thing to is that, okay, you first define your physical system well. After that, you identify what is your symmetry group of transformations. So like, for example, here I've identified the symmetry group of transformations like this. So for some other problem, suppose you had this kind of an arrangement. So let's say that I had 4 atoms which are at the corners of a square. Then in that case, obviously this will not be the symmetry group, it will be another symmetry group. So identify therefore firstly, once you have defined your physical system, identify the symmetry group of transformations. Then after you do that, you also know what is a vector space, which you are typically you can figure out a natural vector space, which I'm putting natural in quotes because the physical system will dictate for you. Like for example, here I will have a natural vector space which is made of the direct sum of the vector spaces of this atom times plus this plus this. This is my natural vector space. So identify that vector space, and then after that, what you do is now represent your group element which is belonging to that symmetry group of transformations by a linear operator, which is going to act now on your vector space. Okay. Or in other words, what I'm going to do is make a mapping from G to this linear operator O of G, which is going to act on vectors which are belonging to the vector space. But what kind of a mapping should this be? Can it be any kind of arbitrary mapping? Because I want to keep the notion of this group properties here.
It should be one-to-one mapping.
More generally, it should be a homomorphism. So this mapping should be a homomorphism, and what we will take it is actually a isomorphism. I mean, actually, I can, what should I say? I can relax it a little bit, but let's make it as an isomorphism. For our sake, let's make it. So I make then a mapping from this to from G for every G belonging to G. So these linear operators. Now we know next that any linear operator, further we know that if I have a linear operator, so if this was a linear operator, I know that I can represent this linear operator by a, okay, so when I write A acting on U equal to V, and I want to find out more information about what this is actually doing, what do I do? When operationally, what did you do? You didn't write it simply as a formal such definition, right? What did you do? You wrote down this. So if I tell you that I want to find out, for example, how the polarization operator acts on vectors for the hydrogen atom. So you write down the operator as X, because the electric polarization operator will be proportional to the vector X. And then you put X, vector X acting on the wave functions. So how do I actually find out, operationally, how do I find out what is this? Changes. How does one define this? Again, this is all recollection of what you have done in your mathematical physics 1. And I know that last semester Professor Limai taught, and he has done a lot of vector spaces. So remember, what did you do? How did you go?
Check the action of the operator on the basis
Elements. Yes. So if I know what the operator does on each of the basis elements, so if I have, for example, this, so if I know what it does on E1, E2, and so on up to, so if I know on the jth element, and for all j's, if I know, so let us say that this gives me some new j's, or j equal to 1 to b. Then what this allows me then to do is, I can find out its action then on any other any arbitrary vector, because any arbitrary vector can be related and can be expanded in terms of the basis. Essentially, what this then tells us is that I can actually, okay, so what this, okay, let me write down these equations. So if I write EJ current is as equal to some equations. Then what you can do is, you can actually find out, suppose I write now, say like, let us say that's EK. And I'm also assuming that we have an inner product space. Okay, so this is going to be EQ. Correct? And then by doing this, I'm going to get now a matrix realization for the operator, which is a D by D matrix. Essentially explicitly evaluating this. So I have to specify this for all. You have to specify what is the action of this A on all the basis vectors. Once I specify that, then after that, what I can construct a D by D matrix, which is this A without the calligraphy there, and the D square matrix elements simply can be obtained from these inner matrices. This, I mean, I'm sure you must have done examples of such things. Or in other words, here what you've done is by specifying this, essentially what you've figured out is a way of realizing this linear operator via a matrix. And essentially that's what we will do here also. So what I can do is, I can ask now, what is rho G acting on this each, for each of these spaces. And if I get this as En, and this Uj again, see this Uj can also be written, see this also can be written in terms of, because it's an arbitrary vector. Now this itself can be written in terms of my basis vectors. So I can rewrite, so let me just write it for this rho J. So it's a linear operator which I made this isomorphism. Then what I can do is, I can rho G, I can act it on this basis vectors, say En, the mth basis vector, suppose I have. And then I can write this as equal to matrix in E. So this gives me, see, I use the matrix A, this gives me the mth row of that matrix essentially. It simply gives me the mth row of that matrix. So, and so by doing this now for all the n's, so do this explicitly for m1 equal to 2 to you, then this gamma will then give me, so this gives me the mn, because you can see that I don't have a summation over m, only this, but I can now, by doing this for all of them, I can get gamma g as a d by d, which essentially is a matrix realization of this isomorphism. But because your isomorphism rho preserves the group property, what it tells me is that, so in other words, your gamma, I can now think of gamma, and so I can also alternately think of directly gamma as a mapping from G to gamma of G for all G belonging to G. So, which is an isomorphism, but now I can think of this as a mapping from the group element G to this gamma of G, which is a d by d. Most generally, it is a d by d complex matrix. So let me just write it. Yeah.
Where work there?
Hi, yeah, not time.
Work there.
So this gamma of G is a d by d. And most generally, because you see, we have made of this matrix elements, it's a d by d complex value matrix. Which will depend on this dimension of your vector space for that physical system. Or in other words, what you have done is, so this gamma, if you look at this, this is an isomorphism from G to what? So the set of all, okay, let me just write this and tell you what this is. Okay, GLDC is the set of, okay, so this denotes the set of all linear d by d complex value matrices, which again forms a group. Because if I take two d by d matrices and multiply them, again I will get a d by d matrix. And if I multiply two complex matrices, two complex valued matrices, I'll again get a complex valued matrices. So this notation stands for general linear, D stands for d by d matrices, and C means that the elements can be complex. So this is just like our O3, SO3. So these are like notations. So really speaking, what you're doing is, and also I forgot, here also invertible. Okay. I also want invertible matrices. But why do I want invertible matrices? Because I know for every G I also have a G inverse. So it will correspond to an invertible. Invertible. So my group property, if I want to preserve the group property, then what I show is that, I have to construct a homomorphism from the group G to this set of all invertible, linear, invertible. Linear is actually redundant, invertible d by d complex value matrix. So what this therefore defines for you, this gamma is therefore defining for you a representation of. So So it defines for you a matrix representation of G. So I have to do this for each G. For all elements, I have to do this. Okay. So if I come back to this example, if I do a rotation here, for example, on the equilateral triangle, then that rotation must be realized as some matrix gamma over some, in this particular case, okay, for every system, there's something called a natural dimension, and here it will turn out to be 6 dimensions because actually it's infinite, but it's 2 into 2 into 2 here, if I just take the xy. So on this space, I will get a 6 by 6 matrix realization, or a matrix realization in terms of 6 by 6 matrices, order of matrices of order 6. And a very important, as I said, very important part is that. So this I'll draw this again later. Your gamma is an isomorphism, so it's a 1-to-1 vertical transformation, and gamma of G, which is now equal to gamma of G. So the group operation, if I'm doing it G, combining H with G like this here, for the matrices, because now I have a matrix realization, the group operation is simply matrix multiplication. So performing first the operation H and then performing G will be essentially saying that if I now think about it acting on my vectors in the vector space, so if I have a U, then I first do gamma H of U. So this will go to some vector U prime, and then after that I again do. Or in other words, what we are saying is that the effect of or the action of a group element is essentially converted into the action of this matrix of on the vectors in the vector space. Right? So I am sort of trying to give you some kind of qualitative way of understanding this, because time does not permit me to get into too much of mathematics right now. But I hope at least you get some picture. Okay, now you can ask the question that, is this a unique realization? Because if you remember, the way I constructed the matrix was through the basis vectors. Because we calculated gamma on each of these basis vectors, each, and then from that I got the rows, each particular row. Fine. So but you also know that for a vector space, the choice of a basis is not unique. I can go from this to another basis. So that means if I have two gammas, say I have gamma G and another lambda G. Both of these are isomorphisms from this an element of the group G to this matrix, to this G and this, suppose. Okay. And if your gamma of G can be written, or if your lambda of G can be written like this. Where S is a similarity transformation. So if I can relate, okay, gamma G and lambda G, if there is a relation between them, where this S is a similarity transformation, then what this means is that these two are actually equivalent representations. Why are they equivalent? Because what does a similarity transformation do on the vectors in the vector space? Or think of, so I know what gamma of G does on the vectors, on these basis vectors. What will this do? Lambda of G, what will it do? Let me put this as S inverse S, for example. What will lambda of G do when I add it on a basis vector?
Ma'am, it diagonalizes the.
Why diagonalizes? Who has told you that this is a similarity transformation which diagonalizes?
It has the same action but in different bases.
So the similarity transformation, this S, is only going to change my basis. It will, see, S will act on this basis set and it will change it to some other basis set. Every similarity transformation is not a diagonalizing transformation. Okay, please remember that. So what the similarity transformation does is just that it changes this basis to this. So if I take lambda g and act it on En, so what it will do is the S part will, so this is like saying that S inverse gamma of G is acting on En. Now SCM is some other basis, so it goes to another basis set. So essentially it's like writing down gamma, instead of writing it in the basis B, you're writing it in another basis B prime, which is related to B through a similarity transformation. So therefore, what you can say is that if two gammas, or sorry, two matrices are related to a similarity transformation like this, then they are not different, they are simply equal. They are known as gamma G and lambda G are equivalent representations. So now the whole, study boils down to then finding out all the inequivalent representations which are. So here I've just taken a particular vector space, but you actually can take more general vector space because I've taken what is supposed to be known as a natural. To illustrate, I showed you for that triangle, but we can ask now. So this D also you can. So mathematically, what you study is that you ask what are the all possible inequivalent representations of your group. And when I talk of all possible inequivalent representations, it doesn't necessarily mean that you are sticking to one particular vector space with only the dimension D. I can get representations now in vector spaces with different dimensions. So like I told you last time, if I take SO3, that is the orthogonal group with determinant R equal to +1, then you will find that I can get representations. Okay, so I'm using now this language. So I can get representations of SO3, which are one-dimensional, which means that they act on one-dimensional vector space. I can get a representation which is three-dimensional, which means it acts on a three-dimensional vector space. I can get representations which are five-dimensional, so which means it will act on five-dimensional vector spaces, and so on. So mathematically, then this is what people actually study in great detail. That what are the all possible representations given a group G? What is the representations, or what are the all possible representations of this group? And the next part is then that how do I characterize representations? Okay, so the classic. So people study how to find out all possible representations. Then how do I characterize representations? That means how do I label them? So if I'm saying that I have, because already you can see I'm saying that two representations are equivalent if you can relate them. But then if I have two inequivalent representations, how do I distinguish them? There must be something which distinguishes them. And this really is a very mathematically quite involved study. There's a lot of rigor. You have to do it pretty rigorously with a lot of abstract concepts and theorems and various other things that you need to do. But what I try to do is just try to give you some, again, as I said, I'm going to go ahead with this, so that at least you build up some kind of an idea of what we are trying to do, or why we want to be, why are we interested in this as physicists. Okay. So without going again too much into the mathematics part, not too much, without going at all into it, I'm just going to give some kind of qualitative feel for what one is trying to do. So now we saw that if I have two representations, as I said, what we want to do is now I can ask the question that can I distinguish two inequivalent representations? Because I said that I can call two representations as equivalent if both if the representations are related by a similarity transformation. So then then the question, as I said, boils down to asking how do I distinguish them, two inequivalent representations? So for that, let me say that given the representation gamma G, okay, suppose I have some representation gamma G. And let us say I have another representation lambda G. Right? Now, without explicitly trying to find out see, so we saw that if I have lambda g as equal to S gamma g S inverse, without explicitly constructing similarity transformations which are relating these two, can I figure out that these two are equivalent? That gamma and lambda are equivalent. Is there a way for me to figure out?
Find trace and determinant of them.
Find the trace in it. So what we will do is now determine it, leave it for a while. So, but if I calculate the trace over representation, okay. So if I calculate the trace over representation, you know that the trace must remain invariant, whether it is for lambda or for gamma. If the two representations are equivalent, then the trace must be the same. Right? So we are going to now give a special name to this quantity. So this is called the character of the representation. And what you know now is that the character remains the same for all equivalent representations, or the character does not change under a similarity transformation. So one thing I can then definitely say is that if I give you two representations, gamma 1 and say gamma and lambda, suppose I give you, please remember this for G. And if I tell you that gamma of G equal to something, say +1, because it's going to be a number, right? Trace of gamma G. Because this is simply going to be gamma I or gamma N of G, N equal to 1 to D. Keep that vector space dimension in mind. Okay? Suppose this is going to be some value, say let's say 1. And let us say that chi lambda of G is say 2. What can you say immediately about these two representations? Immediately you can say that they must be inequivalent representations, because the characters are different. So if the characters are different, then you immediately know that the two representations are inequivalent. On the other hand, if the characters are the same, then we have to think a little bit more. So at least I have now one number or one way of quantifying whether a particular, whether two representations are equivalent or not. And further, what can, as I said, what you can do is, one can show, as I said, that a group can be partitioned over what are known as conjugacy classes, different conjugate classes. And for each of these conjugate classes, what one can show is that the character remains the same. So, calculating the character of a representation is a very important part in studying in these representations, because knowing the character will actually tell me a lot about the nature of your representations of the group. And let me go ahead a little bit more. Now further, suppose I have this gamma. Okay, let's. So this character turns out to be a very important way of characterizing representations. Now gamma we saw was a dividing matrix. Okay? So it's a dividing matrix. Now let's assume that suppose I can write my gamma. So most generally gamma will have all kinds of elements here. It will be, you will have a gamma 1, 1, gamma 1, 2, like this, gamma 1, D, and here this is gamma 2, 1, gamma 2, gamma 2, right? And so on. Now, but suppose it's possible for me to block diagonalize it. So that means what I do now is, suppose I can make some transformations. I started with some basis. But let us say that by making similarity transformations, I can block diagonals. Okay. So let's say that this, for example, let us say, okay, let's say that D equal to 6. And let us say that I make this, so I'm just giving you this example. So suppose I can write my gamma in this form. But this is gamma 1, 1. Gamma 2, 2, then I have here gamma 3, 3, 4, gamma 4, 3, 4, 4. Suppose I can write it like this. For a 6 by 6 matrix, suppose I can do it. Suppose I can write this. So this is an example of a block diagonal form because see, it's not like I've completely diagonalized it, but I've done some kind of a block diagonal. So here these have become 1 by 1, and these are now like 2 by 2 matrices. Because you can see this is 2 by 2, this is 2. So we're making suitable linear transformations, suitable similarity transformations. If I start with some gamma, which means I started with some basis for my vector space, but I have brought it down to this form. And I am not able to diagonalize this any further, neither can I diagonalize this any further. Suppose I cannot do that. It's not possible for me to bring this down. Then in that case, you can see that I can write my gamma like this. So suppose I've done this, then my gamma essentially can be written as a direct product of this gamma 1, 1, this plus gamma 2, 3 plus this particular one. So let's call this as gamma 3. So let me call this now as gamma 1. So let's call this like this, gamma 1, gamma 2. This one I'll call it as, this is gamma 1, this I'll call it as gamma 2. This whole thing I'll call it as gamma 3, and this I will call it as gamma 4. So I can write this as a direct sum of these numbers. So these are one-dimensional objects because they are just one element here, but these are now 2 by 2 units. So basically I keep on diagonalizing till I go to the limit. That means I have only reduced this. I cannot diagonalize any further. I'm not able to diagonalize. I have to leave it at this form. Then if I bring it to this form, then in that case, these gammas, so gamma 1 G, gamma 2 G, gamma. So I brought it here like gamma 4, for example. In this particular case, I got gamma 1, gamma 2, gamma 3, gamma 4. And these are called as irreducible representations. Representations of. See, essentially what has happened is, once I bring it into this form, what is the meaning of this? The meaning is the following, that I started with the 6-dimensional vector space. So I started with dimension B is equal to 6. But if you look at this is going to act only on a 1-dimensional vector space. Similarly, this will act only on a 1-dimensional vector space because you can see that this part is all 0 and this part is all 0. While this particular gamma 3 will act on a 2-dimensional vector space, this is going to act again on a 2-dimensional vector space. Or in other words, my vector space B, what I have done is I have written this in the form of a 1-dimensional vector space, a direct form of another 1-dimensional vector space for this, plus a 2-dimensional vector space, another 2-dimensional vector space. So my vector space itself has been broken up into a direct sum of vector spaces which are smaller dimensions. And these are invariant subspaces with respect to gamma. Each of this is invariant. Why is it invariant, or what do I mean by saying it's an invariant subspace? Because if I'm in this subspace, for example, which corresponds to the vector space for this, the action of gamma on any vector inside this vector space, which is made from these basis vectors corresponding to 3 and 4, it will only take to a vector inside this space. It is not going to take you to a vector here or here or here. Alright. So in that case, essentially what we are saying is that the action of gamma on any vector which is lying in one of these invariant subspaces remains or transforms into a vector which remains in that same space itself. So that's why we call it an irreducible representation, or because you can't go further down. Or in other words, you started with a 6-dimensional vector space, which now we will say is that. So if I started with the most general gamma, which is like say where all these were there, gamma 1, gamma 1, gamma 1, 2, gamma 1, 6. For this, I'm just taking with this example here, gamma 6, 1, gamma 6, 2, gamma 6, 6. If I write it like this, where they are not 0, I have not brought it down to this form. So let's say I started with that basis B. Then the fact that I can bring it down from here to here by doing a set of similarity transforms tells me that this is what is known as a reducibility transform representation. So the gamma 6, this gamma is reducible to a sum of these irreducible representations. So in this particular case, I have been able to reduce in quotes. So I'm reducing my gamma to a sum of 4 irreducible representations. Gamma 1, gamma 2, gamma 3, gamma 4. In this case, okay. And when I say it's an irreducible representation, what it means is that I cannot go, I cannot construct any more invariant subspaces inside that subspace. So as I said, the theory, okay, so again, let me go back to what we want to do therefore. So we mathematically, therefore, we want to find out all possible representations, but then now I can boil it down to finding out all possible irreducible representations. Because if I know all the possible irreducible representations, then I'm done. Because any other representation can be simply constructed as a direct sum of these. And we have already seen that for any representation, I can use a character to distinguish, or it's going to be a characteristic trait of a particular representation. So construct all or try to find out all the possible irreducible representations and the corresponding characters for that representation. And this example also tells you, okay, let me just write it again. So this gamma, when I brought it into the block diagonal form, it was gamma 1, 1, gamma 2, 2. Then I had a gamma 3, 2, 6, gamma 3, 4, and I had gamma 4, 3, gamma 4, 2, and then I had a gamma 6. You can also see here now that I have got here, these both are one-dimensional representations. And these two are both two-dimensional representations. Both of them are dimensional. They are going to act on vectors where they are two-dimensional, while these two are going to act on one-dimensional representations. So typically then I can say that given a representation, so I can write my gamma now. So I'm going to write it the following way. So I can write it as gamma 1. Most generally, I can write this as direct sums like this. Gamma D, or sorry, gamma SC. And I will also write this corresponding numbers here into to tell you that how many times it can happen that the same thing occurs here. See, I've written this as if these are inequivalent because most generally I don't know whether gamma 5, 5, 5. But it might happen that the same numbers appear here. Or these two may be the same. In which case, what it means is that the same representation has occurred more than once. Okay, so it's possible when you do this diagonalization or what this is called as the block diagonalization. So when I do this block diagonalization procedure, it's just like when we do a diagonalization of a matrix, I can get the same eigenvalue more than once. Similarly, I can get the same block diagonal form more than once. So these n1 into ns, they are what are known as the multiplicity of the irreducibility. And usually for irrep, it's called as IR, irreducible representation is short form. So this is a block diagonal form for So construct the gammas, write it down in terms of these irreducible representations, and also it's important to know what is the multiplicity for each representation. All right, now what I'm going to do is, then as I said, what you do next is calculate the characters for each of these irreducible representations, because if I do this, then I sort of know at least something about characterizing each of these. And then there are some theorems which will actually relate characters. So if you have a finite group, then what one can relate characters to the order of the group. So for example, when we had our TM group, it was an equilateral triangle group. There the order of the group is 6 because it was a 6-element group. So there, okay, let me just mention something. Now, what one can show is the following, that so suppose I have some irreducible representations, okay? Now let us say that I have, okay, so given a particular group, let me say that I have S irreducible representations, okay? Just like I wrote down. So suppose my gamma can be written as equal to N1 gamma 1 plus, this is the multiplicities, and into gamma 2 plus into gamma 2 plus N1. So now I can construct the characters for each of these. So chi1 will be, so I can write down chi1 of G. Please remember that I'm suppressing, but there's actually a G part here because I constructed dimorphism, and I'm doing this for each element G. And I define this chi1 of G as equal to, say, raise of gamma 1 of G. Or more generally, I can say chi k of G is raise of k equal to 1. So this will give me a set of elements, chi1, chi2, chi3, scalar numbers. Now think of each of these numbers, chi1, chi2, chi3, up to chi-s. So think of this column as an S-dimensional vector. So I can get, so given this particular block diagonal form, calculate the characters and think of each of these as a component of a S-dimensional vector. And then for a finite group, you have a very interesting relation that, and because this gamma is after all a matrix realization, I mean, it's just the matrix elements. In general, this size can be complex also, most generally. And one has some very interesting, I mean, there are some nice theorems which tell you that this, for example, let me write it down and then. Okay. Here Ng is, so for a finite group, Ng is equal to the order. You have interesting relations like this, that if I sum over the characters, so it's, see, this is like chi q star, chi k g. Okay, so it's like as if I'm taking this and taking the corresponding row. It's like doing this kind of thing. If I think of this, something like that. And then I'm summing over all the group elements here. Remember that. Okay. Then in that case, you have got what this is known as an orthogonality relation for the characters. So the characters, if I think of as vectors, so if I have, say, I've brought it down to this is number of irreducible representations, and for a finite group, you can also show that the number of irreducible representations is always finite. That is also something one can show. And then if I calculate the corresponding characters, then the characters satisfy a certain orthogonality relation, which is represented like this. Again, I want to mention that these are the characters for the irreducible representations. And you can then also show the following, that the multiplicity in K for a particular, so now I can, from this relation, one can actually show that the multiplicity is given by G. I'm doing all this without any proofs. So I can think of it as I start it. So it's like projection of this into that. So this is really like chi. So when I'm writing the graph that, I'm just taking it. Now in this, you think about it as a vector, again, S dimensional vector. So I am chi S equal to chi 1, so chi 1, chi S. So this is my K chi, and then the corresponding graph will be chi 1 star chi. So this graph will be that is chi 1 star. So I'm here using also the orthogonality. Once I use this orthogonality relations and then do this, you can find out what is the multiplicity for a particular irreducible representation. Because it's very important not just to know what are the irreducible representations, but also you have to know how many times it occurs. All right. Now I'm just going to sort of not tell you much about how I got these answers, but I will show you this now for our drawing, for our equilateral drawing. How many reducible representations we have, and then see. Okay. So if you look at this, yes.
Ma'am, we have a lecture now.
Yeah. Where are you? 12:30.
Okay, fine. I'll stop here. So I'll continue with this on Thursday then. Okay. And I'll also do a few more problems on tensors on that day. Because I just want to illustrate now whatever I've told you about this representation for the for that equilateral triangle. I will also say that it's related to your ammonia molecule. So there's really a physical reason for doing this.
Ammonia major.
Oh, okay,
Light लगा दो. Ammonia major, na?
I'm actually going to do the vibrational modes.
Okay.
I mean, how to get the
Ammonia major.
so there you need the frequencies, no?
Yeah.
The
24 gigahertz.
what are the degenerate breathing frequencies?